Welcome back, everybody, to our little conference. Really appreciate everybody joining us. It's really good to have everyone again. And this morning we have Stephen Lynch speaking to us about collapsing and non-collapsing ancient solutions. Over to you, Stephen.
Thanks a lot. Thanks for having me. So yeah, I'm going to talk about some results about ancient solutions, but kind of the point of these results is to shed some new light on singularity formation in mean curvature flow of hypersurfaces in Euclidean space, which might have some self-intersections, so they're not necessarily embedded. So let me just quickly, set that up, and this will sort of, indicate why the results that I'm discussing about ancient solutions are sort of interesting. So I'm going to begin with an immersion, which has positive mean curvature. So it's mean convex, meaning H is positive, and this M is a compact smooth manifold. And then let F be the maximal evolution of this immersion by a mean curvature flow. Okay, so this family of immersions solves this evolution equation where nu is the normal, the unit normal. And I want this to agree with F0 at the initial time. And we know that this solution of mean curvature flow is going to form a singularity at the maximum time t. And at this singularity, the mean curvature is going to become unbounded along some sequence of points. So let's choose such a sequence where H is becoming unbounded. And the sort of typical method for trying to reveal the geometry of the solution in a neighborhood of this singularity as it's forming is to do a blow up. And by this, I mean that we define a sequence of shifted and rescaled solutions, which I'll call Fk. So we want to scale the solution by lambda k, scale the time variable accordingly so that it remains a solution, and shift in time and space in such a way that this new sequence is anchored at the origin in the ambient space at time 0 and has mean curvature normalized at that point. And this rescaled solution is defined for minus lambda k squared t up to time 0. So in particular, the time interval on which it's defined is getting longer and longer. And I'm going to suppose that this sequence is converging smoothly to some limiting solution, which is then called a blow-up limit. So suppose that Fk is converging to some F bar smoothly, where this F bar is just some ancient solution of the flow, and it no longer, is necessarily compact, but I'm going to assume that it's complete and that the convergence is all the way out to spatial infinity. So this F bar is a complete ancient solution. Okay, so there are situations where this convergence is known to hold, and there are other situations where it's not known to hold, but I'm not worrying about that yet. I'm just simply saying, suppose that we have convergence. And then we know by a result of Huisken-Sinistrari that this limiting flow F bar actually has non-negative second fundamental form. Okay, so we assumed that the initial immersion F0 had positive mean curvature. This is preserved by the flow, and the work of Huskyn-Sinistrari tells you that you have this property of the blow-up limits, that the second fundamental form is non-negative. Okay, and their estimate really works whether you're immersed or embedded, but there's another approach to proving this statement by Brian White in case the solution happens to be embedded. But in any case, this is what's usually referred to as the convexity estimate. But notice it doesn't quite tell us yet that our blow-up limit is actually convex, in the sense that at each time the hypersurface bounds a convex body. At the moment, we only know that the second fundamental form is non-negative, which is sort of a strictly weaker condition. But if we assume a little bit more about the original solution, then we can conclude that, this blow-up limit is indeed convex. And the way to do this is to say that our immersion F0 actually has positive scalar curvature, say, rather than just positive mean curvature. So if we assume this, so let me denote the scalar curvature just by R, then because of compactness, we can find a constant beta, say, such that the scaling invariant ratio R over H squared is greater than or equal to beta at the initial time, but then a maximum principal argument tells you that this actually holds up until the maximal time. Okay, and because this inequality is scaling invariant, it carries over to the blow-up limit F bar. So under this additional condition, we know that this F bar solution actually has positive scalar curvature if it has positive mean curvature, which is the case as long as it's non-trivial, as long as it's not, flat. So we conclude that F bar has positive scalar. But now it's sort of, right now, what do we know about this F bar? We know that at each time it's a complete hypersurface, which has non-negative second fundamental form and positive scalar curvature. And so there's a classical result by Zuckstetter, which tells you that, in fact, every such hypersurface is the boundary of a convex body. So now we can conclude that at each time F bar M bar T is the boundary of some omega T, where this is an open convex set. Okay, so we have a compact solution of mean curvature flow, assume it's got positive scalar curvature at the initial time, and then if we can extract smooth blow-up limits at a singularity, then they actually have to be convex ancient solutions, in the sense that at each time the hypersurface bounds a convex body. And so for this reason, it's interesting to look at convex ancient solutions of the flow. And in particular, one thing you can try and do now to get an idea for the geometry of the solution near a singularity is to try and classify the ancient solutions that actually occur as blow-up limits in this way. And there's been many sort of spectacular breakthroughs in this kind of endeavor in recent years. But, most of these results assume a condition called non-collapsing. So let me just write this. Okay, so what does this non-collapsing condition mean? It just means that if you go to some point X on your hypersurface at time t, and look at the largest ball, which is contained in your region omega, then the radius of the ball should be bigger than alpha over the mean curvature at the point x at time t. And this constant alpha should be uniform across all points in space-time, in which case you say your solution is alpha non-collapsing. And the reason, I guess, that the many of these classification results, make use of this condition is because solutions satisfying this have very good compactness properties. So in particular, you have the global convergence theorem of Haselhoff-Kleiner, which lets you take, essentially arbitrary limits of solutions satisfying this condition, and is really useful for probing the shape at time minus infinity or out at space infinity, and for getting a grip on the geometry of these things. So this is an extremely useful condition, and it is indeed satisfied for blow-up limits of the flow in a number of situations. So for example, if F0 is embedded, and H is positive, then in fact all blow-ups are non-collapsing. And this was first, sort of proven by White, and then proven in a different way by Sheng and Wang. Both of these approaches really use blow-up arguments and the convexity estimate, but there's another approach by Ben Andrews, which is purely by the maximum principle. But then one can ask the question, like, if we no longer assume embeddedness, if we allow F0 to have some self-intersections, then is this still true? And the answer is a clear no by an example of Anganen. So he showed that if you can take sort of curves in R2 with self-intersections, which have positive curvature everywhere, but when you evolve them by mean curvature flow, this sort of inner loop will pinch off in a kind of cusp singularity. And when you blow this up, what you see is a Grim Reaper solution. And this is somehow, the sort of quintessential collapsing convex ancient solution, because if you normalize it to have curvature roughly equal to 1 at the tip, then it will lie in a strip of width pi, but these arms are asymptotic to straight lines, so the curvature is very small here, meaning that, the ratio of the inscribed radius pi to the curvature kappa is extremely large, right? So you don't get this alpha non-collapsing property for any alpha. So this is the Grim Reaper, which is collapsing. Okay, so if you allow self-intersections of the initial data, then you can get collapsing blow-up limits. But, and of course, this example is only in R2, but you can get similar examples in higher dimensions just by taking a long, thin torus over this curve. And what you'll see in that case is blow-up limits, which are modeled on a Grim Reaper times, a hyperplane. So if you take a long, thin torus over this kind of self-intersecting curve, then you can extract blow-up limits, which are like Rn minus 1 times the Grim Reaper, okay, if your original solution was n-dimensional. So you know, the next question you might ask is, well, is there any further condition we can place on the initial data which might rule out these collapsing blow-up limits? And the thing to notice, I guess, is that all of these, you know, examples that I've written down have zero scalar curvature because they only have one non-zero principal curvature. And in order to have any scalar curvature, you need to have at least one product of principal curvatures, which is non-zero. So these all have zero scalar curvature. And, you know, naively, this might lead you to conjecture that if you assume positive scalar curvature, then you actually do get non-collapsing of blow-up limits, right? Maybe in some sense, these examples are the only ones. This is the only thing that can go wrong. And this is exactly what we were able to verify. So the result that I want to talk about for, you know, the rest of my time with Theodora and Matt which we did last year, says that if we take a convex ancient solution and we assume this kind of scalar curvature pinching condition, which I, you know, already had above, then in fact, this solution is non-collapsed. Okay, so in particular, if F0, so our initial immersion for the flow, which might have self-intersections, if this has positive scalar, then all blow-ups of its singularities, if they exist, must be non-collapsed. This is essentially optimal because these examples I described above, where you take a long thin torus over a curve, you can make these so that the scalar curvature is arbitrarily close to zero. So there's sort of counter examples living on the boundary of this condition. And this is great because it means that you can take all of the classification results which have been proven for non-collapsing convex ancient solutions and, you know, carry them over to this setting where your solution might in fact have self-intersections. So that works out quite cleanly. So for the rest of the talk, I'm going to basically describe, you know, a sketch of how this is proven, and then at the end, give some applications. But I guess it's a good time to pause if anybody wants to make a comment or a question.
I guess there was a little confusion here about what you meant by a torus over the curve. So maybe just clarify that.
Oh yeah, I can try and draw it. If you have the curve like this in R2, I mean, basically what you would do is, you know, try and rotate it around an axis in R3. So you would get sort of something like this, right? So like a long torus where instead of the cross section being a circle, it's this curve with the self-intersection. And sort of, I guess by a long one, I mean one for which this radius of the outer circle is very large. So all that does is it, you know, in this case, you would have two principal curvatures, one of them coming from the long circle factor, which is very small, and the other one coming from the self-intersecting curve, which is comparatively very large. So under the flow, its behavior should sort of dominate. Yeah, does that clear it up?
Yeah, perfect. Thanks, mate.
Okay, so we want to try and prove this theorem that some scalar curvature pinching for a convex ancient solution actually implies non-collapsing. And it's actually really two parts put together. So the first one says that if the domains enclosed by your solution sweep out the ambient space, then the solution has to be non-collapsed. So this condition here is what it means to sweep out the ambient space. This implies non-collapsing. And the second part is to show that if you don't satisfy this condition, so, or rather, if you satisfy the scalar curvature inequality, then you actually have this property that you sweep out the whole space. Okay. So I'll try not to get bogged down by too many details, but just give, a fairly good idea of how each of these parts is established, beginning with part one. And so the crucial tool here that we make use of is the arrival time. So let's fix a convex ancient solution with time slices omega t. And define its arrival time in this way. So u at the point x is the supremum of all times for which x is in omega t. Okay, so this means that if the boundary of omega t reaches x, then u of x is exactly the time at which this happens. Or in other words, the time slices of the solution are just the t level sets of this function u. So this encodes the whole solution in a function which is sort of one dimension higher. And to see what this looks like, we can take the example of a shrinking sphere solution, Sn of radius minus 2nt. And in this case, your function u is just x squared over 2n. So with a minus sign, right, with my sign convention. So this is a negative paraboloid with level sets equal to the time slices of the shrinking sphere solution. And this turns out to be an extremely useful object for these convex ancient solutions because this function u is itself concave. So if all of these time slices are convex, then u is actually a concave function. And the ingredients that you need to prove this are one, a result of Suja Wang, which says that if you're a compact convex ancient solution, then you have concave arrival time. This is proven by a maximum principal argument. So this is Suja 1. Second ingredient you need is a statement due to Daskalopoulos sires, which says that if you have a convex hypersurface, then it actually has a unique evolution by mean curvature flow, which is kind of remarkable because they don't need a full curvature bound, right? Only a one-sided curvature bound in the form of the convexity assumption. Right, and so with these two ingredients, you can prove the lemma because what you do is you take a very early time of your convex ancient solution and approximate that time slice by compact convex sets, and evolve each of those by mean curvature flow. Now, for each of those compact evolutions, you have an arrival time which is approximately concave. And as you take the limit approximating your non-compact solution by the uniqueness result of Daskalopoulos Sayers, you actually get back the original guy. And because the approximators are approximately concave, that means that your original solution is approximately concave, at least after that very early time. And then sending that early time back to minus infinity, this approximate concavity becomes actual concavity. So I don't know if that made sense, but the point is that with these two ingredients, you can do an approximation argument, which lets you conclude the lemma. Okay, so once we know that the arrival time is concave, then we can establish very powerful compactness properties for solutions which satisfy this condition of sweeping out the entire ambient space. In particular, we can show that if we have a sequence, and each of these sweeps out the ambient space, and we know that they're anchored at the origin at time 0 and normalized so that the mean curvature is equal to 1 at that point, then these solutions actually subconverge to some limiting flow in C infinity on compact subsets of space-time along a subsequence. Okay, so this kind of compactness property is known for solutions which are non-collapsing, but we're not assuming that, right? All we're assuming is this condition that you sweep out the ambient space, and in fact, you still have exactly the same compactness properties under this condition, and that is really the thing that eventually lets you prove the non-collapsing for these kinds of solutions. So once again, let me just sort of give the ingredients.
So doesn't compactness also follow from the Harnack inequality? Or?
The Harnack inequality?
Yeah, I mean, if you have convex solutions, then you have the Harnack inequality that also should give you a very good compactness.
Yeah, I mean, I'm not assuming that they have bounded second fundamental form. So I guess you can't apply Hamilton's Harnack inequality out of the box.
Well, I mean, you could do the same doubling trick that you just explained.
The same argument, right? That's right. And so it turns out that this concavity of the arrival time is equivalent to the Harnack inequality. So you're exactly right. By the same argument, you get Harnack. So yeah, I mean, I suppose you could argue that way as well. Yeah, that's a good point. I didn't think of that. So thanks for pointing that out. But anyway, let me describe the argument that I was thinking of. So here you now that you know that the arrival times are concave, there's another result of Su Zhao Wang which says that there's a universal constant C, such that the arrival times UK of all these solutions satisfy a uniform estimate like this. Okay, so all this means is that there's a paraboloid with a uniform constant C, which sits underneath all of them. And one way to think about this is, I guess, that these solutions, their blowdown should be a shrinking cylinder. So that's roughly sort of where you get this uniform parabolic behavior at time minus infinity. But in any case, he proved this kind of uniform estimate. And so now you have a sort of a sequence of concave functions like this, and they all have a uniform paraboloid sitting underneath them. So none of them can be too steep anywhere, right? Otherwise they would cut in to this paraboloid. So in fact, for all of these arrival times UK, you get a Lipschitz bound. And so you can at least pass to a subsequence where they're converging, like in C0. So let me write that. But once you have, the C0 convergence of the arrival times, then if you look at the level sets, these are, solutions of mean curvature flow. So using parabolic regularity, you can upgrade this to smooth convergence of the solutions. Okay, but yeah, the point really is that once you have the concavity of the arrival time, that sort of gives the arrival times good compactness properties in and of themselves. And then that combined with parabolic regularity gives you this nice smooth compactness theorem for flows which sweep out the entire space. And with this compactness lemma, the non-collapsing that we wanted to prove follows basically immediately. So So I'll try to just explain this in words as well. If we have, if the statement is not true, then we could find a sequence of solutions which sweep out the entire space, but for which this non-collapsing ratio is degenerating at some point. That's along some sequence of points. And so if we take those degenerating points and put them at the origin and rescale to make the mean curvature 1 there, then by our compactness lemma, we should have smooth convergence to a nice convex ancient solution. And in particular, these domains whose non-collapsing is supposedly degenerating have to be converging to an open convex set. And so these two things can't be happening simultaneously, right? The smooth convergence automatically gives you a lower bound on the inscribed radius at the point where you've normalized. So you get the non-collapsing immediately from this kind of compactness contradiction argument. So that's how you get part 1. And if there's no questions or comments about that, then I'll quickly say something about part 2. So we've showed that if you sweep out all of space, you have to be non-collapsing. And the point now is to show that if you have this kind of scalar curvature pinching, then you have to sweep out all of space. And so here again, we use a result of Suzhou Wang, which tells you that if you don't sweep out all of space, then the region that you sweep out has to be a slab. Okay, so by a slab, I mean the region between two parallel hyperplanes. And so the quintessential example of such a solution is, of course, the Grim Reaper, which we saw in the beginning lies in this strip of width pi. So now we're going to suppose we have a convex ancient solution which sweeps out a slab. And we're going to argue that there has to be a sequence of points along which this ratio, scalar curvature over h squared, is actually going to 0. And this will prove the statement by contraposition. So let me just show you the n equals 2 case, because the higher dimensional case is basically the same, but this is easier to draw. So let's let n equals 2. So we're looking at evolving surfaces in R3. And we're assuming that the omega t sweep out a slab without loss of generality. We can assume that this slab is given by absolute value of x3 less than or equal to some constant c. And now what we do is we take the middle plane of this slab and consider the solution intersected with that, which is just going to give us a nice convex region in R2. So let me call this omega t tilde. This is the intersection of omega t with x3 equals 0, which you might draw like this, right? So this is omega t tilde. And now we can fix any sequence of times going to minus infinity. And just let our point xk be the point in this boundary whose distance to the origin is minimal. Okay, and the point is that by choosing xk in this way, we ensure that there's a disk dk which is contained inside the region omega tilde and which touches the boundary at this point xk. And moreover, because these domains are sweeping out the slab, these disks dk are going to sweep out R2. So they're getting arbitrarily large as time goes to minus infinity. And the basic idea now is to take these points xk, tk, shift them to the origin and rescale and extract a limit, and argue that because these disks are blowing up, the limiting solution has to split off a line and therefore has 0 scalar curvature, which is exactly what we're trying to show here, right? This is what we want our sequence to do. And so this works perfectly nicely if you know that there's some positive constant delta such that the mean curvature at these points is bounded above and below in this way. So suppose for a minute we knew this, right? Then if we shift xk, tk to the origin, then since these disks dk are sweeping out all of R2, then we extract a limiting flow let's call it omega hat t, or maybe omega infinity t is better, right? So in the limit, if you look at the intersection of this with the middle plane, this is going to contain a half space. Okay, but it's also convex. So if you're convex and you contain a half space, then you have to be a half space. So in fact, this set is a half space. Okay, so in particular, the solution, omega infinity, it splits off a line. And since we're in dimension 2, the other thing that you get is just a solution of curve shortening flow. Okay, but this object only has one non-zero principal curvature. So its scalar curvature vanishes identically. Okay, which is exactly what we wanted to show. So I made some assumptions here, right? I restricted to n equals 2, and I assumed that, you know, this curvature bound holds, which is a little bit unjustified for the moment. But this is the basic idea, right? To use the fact that you're sweeping out a slab to find some points along which you can extract a limit, which splits off so many lines that it actually has zero scalar curvature. And in general, if you choose the sequence xk tk in the way I did, then you don't necessarily get these two curvature inequalities. But in the paper, we show how to do a point picking argument to ensure that these are actually satisfied. And in order to do this, you have to move the point xk a little bit away from the disk, but it turns out that you don't have to move it far enough away to derail the argument. So it's a little bit complicated what you have to do there, but you know, it's sort of elementary in the end, just fiddling around with this sequence so that things still work out. So let me just write that, ensure that this holds by point picking. And the n, or the higher dimensional case is you know, analogous. Okay, so going back just to remember what we're actually proving, we wanted to show that if you have this scalar curvature pinching, you sweep out all of space. So we assumed not, therefore you sweep out a slab, therefore you find a sequence of points where this you know, inequality is degenerating. And that proves part 2 of the claim. So now putting parts 1 and 2 together, we get the result which I stated in the beginning, saying that all convex ancient solutions with this kind of scalar curvature pinching are actually non-collapsed. So now there you know, should be a few nice applications of this result. I said in the beginning that I was just, you know, to motivate this problem, I considered initial data which had positive mean curvature, but possibly self-intersections. And I said, let's look at a blow up of a singularity and assume that the blow-up sequence actually converges smoothly. But in general, we don't know that this is the case. We know that we have convergence if the initial data are embedded. And by work of Keaton Naff, we know that we have convergence if the initial data are too convex. But if you weaken this to something like 3 convexity or even further to positive scalar in higher dimensions, then it's not yet clear at all, right, how to actually prove convergence of these kinds of blow-up sequences. And this is exactly what I'm now trying to rectify with Naff. So this is together with Keaton Naff. And it might seem a little bit weird, right, that we first, are studying the blow-up limits and then trying to prove that they exist, but it sort of makes sense. I mean, I guess it's not so different from the situation that you often have with PDEs, where you first prove some a priori estimates and then use those to prove existence for a given problem. And this is kind of similar. I mean, I guess what we've done is proven a priori non-collapsing estimate for blow-up limits, and now we're trying to use that to show that the blow-up limits actually exist. And there's some precedent for this kind of approach in the work of Perelman in Ritchie flow, for example, where he first proves some properties of kappa solutions and then uses them to actually show that blow-up limits converge. So this is one nice application that we're hoping to get out of this. And this sort of similar problem is to prove gradient estimates for fully nonlinear flows of immersions. Okay, so the first step towards this is to take everything I just described and generalize it to more general speed functions, where you're evolving not by the mean curvature, but by perhaps some concave function of the second fundamental form. But this more or less works because, most of the arguments just use, the maximum principle and so on, things which have an analog in the fully nonlinear setting. And so once you've done all that, you've got the a priori non-collapsing estimate for convex ancient solutions. You can try and use that in the same way to study blow-up limits. And there was sort of a nice paper a few years ago where Simon Brendler and Gerhard Husken used a fully nonlinear flow of 2 convex embeddings to classify these kinds of hypersurfaces in certain Riemannian ambient spaces. But they really did need to assume embeddedness. So they used the non-collapsing estimate for the inscribed radius to get a gradient estimate, which they then used to perform surgery. And this sort of left it completely unclear how to get a similar gradient estimate if you're only immersed. But this kind of result for ancient solutions that I've been describing seems to be exactly the ingredient that you need to do that. And so this is something else that I'm now working on with a view towards getting a topological classification for 2 convex hypersurfaces in Riemannian manifolds that might have self-intersections. I think I'll stop there. So thanks a lot for your attention and thanks for inviting me to speak. I mean, it's a great honor.
Thanks, Stephen. Look forward to seeing those applications.
Can I ask something?
Go ahead.
The way I think about non-collapsing is to show that the tangent flow at time minus infinity is not a multiplicity 2-plane.
Mm-hmm.
Been wondering, can one understand your proof in terms of the tangent flow at minus infinity?
I believe so, because I guess this dichotomy that I had where you say either the solution sweeps out a slab or it sweeps out the whole space, you can also show that it sweeps out a slab if and only if the blowdown is a multiplicity 2 hyperplane, and it sweeps out the whole space if and only if the blowdown is a shrinking cylinder.
Oh, I see. So maybe I'm not asking a question about your paper, but the paper by Shushavang, maybe.
Exactly.
The dichotomy. Do you have some good way to understand that? Why? I mean, if the tangent flow is minus infinity is a multiplicity 2-plane, then still has to prove something that it's just a slab and doesn't sweep out the whole space. How does that work?
Yeah, that's right. I mean, he proves this amazing estimate, right? Which tells you that if at some time you are contained in a thin enough slab, then in fact you're contained in a slab for all times. And this is by sort of a remarkable iteration argument, which I think is really like the key insight in that paper and the driving force for everything that he does. And it's still a little bit mysterious to me. I mean, at some point there's a kind of integration by parts in there, and then it's a bit magic, I think.
Yeah, you could sort of think of it as like a Liouville theorem, where if you have if the growth of the width is less than a certain rate, then it's actually bounded. But that doesn't help understand the proof at all. Yeah, I think Ben had a question.
Yeah, no, I was going to ask. So you're assuming positive scalar. Can you weaken that to n-1 convex?
Yeah, that's right. So I mean, that would really be the right condition. I don't really know why I made it positive scalar. I think I'm just tired.
Oh, okay, fine. But there's no real obstacle to doing it, I guess.
No. I mean, in the paper, it's all written up in terms of n-1 convexity.
Oh, I see, right.
But often when I talk to people about this condition, they go cockeyed, right? But they sort of know what positive scalar is. So.
Fair enough, yeah. This last application you're talking about would be the same flow, presumably the harmonic mean of the sums of two principal curvatures, yeah.
Okay, then thanks again, Stephen. Very nice talk.
Thanks a lot.